Hello everyone, welcome to our discussion of section 7.1, where in this course for the first time we will begin our discussion of probability concepts. So this will be the first lesson in a series of lessons, and it will mainly involve the definitions we should know before manipulating other values of probability. So it's mainly, this lesson mainly going to be about knowing definitions and notations and so on. Okay, so we will begin with the very important thing that we should know about probability, which is probability values range from 0 to 1. So let's put that in writing, probability values range from 0 to 1, and this is such an important thing to remember. Okay, so it's important because if you're calculating probability in any of the homework assignments or the upcoming exams, if you get a value that is negative, let's say minus 0.2 or minus 0.1, then you know you did something that is not correct in your calculation. So you want to go back over your steps to see where there is an error. Or if you come up with a value that is over 1, say 1.8 or 1.3 as a probability, again you know that the calculations are not correct. So in mathematics or statistics, we'd like to quantify things. One of the things we'd like to quantify is uncertainty, and probability is a measure of uncertainty. Okay. All right, so here is the first set of definitions that we need to know. And this is the definition of a set. What is a set? Collection of things and or people. It could be anything. It could be a bunch of fruit, people, things, cars. A set is a collection of things or people. And you can define what that collection is. Okay? It could be anything. And so here are some examples of sets. And by the way, usually we denote a set by a capital English letter. Okay, so suppose set A represents this collection of numbers. Suppose we define another set, let's call it B, and this is a bunch of fruits, so oranges, apples, kiwi, and pineapple. Okay, so that's another set. What would be another set? Well, collection of people, a specific people. So Tom, Jane, and let's say Max. Okay, what else? What kind of other examples can we have? Well, all of these three examples that I've given so far are examples of finite sets. Right? So they have a finite number of members. This set has 6 members, this set has 4 members, this one has 3 members. But a set can also be an infinite set. So say 0 to 4, 6, and then if I put 3 dots, that indicates that this set on this side has no end. In other words, it'll go on. So this is an infinite set. So we can label these that, and that. These are examples of finite sets, and that one is an infinite set. And let's give another example of an infinite set. So another example would be, let's say, this time. So this set was infinite on one side. Let's make it infinite on both sides. So this side, and we have -3, -2, -1, 0, 1, 2, 3, and then infinite on both sides, right? So this and that one, these are examples of infinite sets, okay? So once we define a set, then we should also define a subset. Okay? And of course, it has its own notation. And so suppose A and B are two sets. Okay? And then the notation, and I want to use one of my thicker markers, the notation A like that notation means that every member of set A is also a member of set B. And the critical word here is that every. So if you have A that has 3 members out of 4 members of B that are similar, but the next member is not similar to B, then A cannot be the subset of B. So if the two sets are different by even one member, then you cannot say that A is a subset of B. So every member of set A must be also a member of set B in order for us to say A is a subset of set B. So, and let me add that. So therefore, A is a subset of B. Right? Is a subset of B. So by the same token, let's see. So let me make a bulleted list here, and so by the same token, this notation, A like that means A is not a subset of B. That means not every member of set A is a member of set B. Means that not every member of set A is a member of set B. So, and the key word here is not every member. So if you have 2, 3 members out of 4 that are similar, it's fine. But if the last term, if one of the members is not common between A and B, then A is not a subset of B. Okay? All right. So let us give some examples of this, just to be sure that this is understood. So if, suppose set A has elements or members 1, 7, and B, set B, it has elements 1, 3, 5, 7, 9, and 11, then what we can say is that, so what do you think? Is A a subset of B? It is, isn't it? Because 1 is here and 7 is also here. So A is a subset of B. Okay? But is B a subset of A? Is every member of B also in A? No, right? So we can say that B is not a subset of A. So it works this way, but not the other way around. Okay? Let's do another example. So if A is equal to 1, 7, and 18, and set B is equal to 1, 3, 5, 7, 9, and let's say, let's say 18, right? Let's say that. Then is A a subset of, well, let me change something here, guys. So I didn't mean to, so let me change this to 28, actually. I wanted to make a point here. So that's 1, 3, 5, 7, 9, and then 28, right? So is A a subset of B? Right? We have 1 and 7, but not 18 is not there, so no. So A is not a subset of B. And how about the other way around? Is B subset of A? Definitely not, right? So B is not a subset of A either. Okay? All right. So that's the definition of a subset. The next definition we need to know is the definition of the empty set. So the empty set has its own notation. So the empty set is sometimes denoted as the letter phi in the Greek alphabet, phi, or another notation for the empty set are 2 braces, curly braces facing each other with nothing in between. So that's an empty set can be denoted with the letter phi. It can be denoted with this 2 empty braces facing each other with empty, in between, with nothing in between, as this or that. The other thing that you should know about the empty set, and I will write this in red because it's very important. The empty set is a subset of all sets. So no matter what kind of set you create, the empty set is always a subset of that set. Always. There is no set that you can create where the empty set is not a subset of that. The empty set is always a subset of all sets. Okay? So for example, if we say that set A is the empty set, right? If that's the case, and B is this set with zero as the only element, and C another set with these and D oops, that's 0, 1, 2, 3, like that, right? If that's the case, then this is what we can say. And then A, which is the empty set, is a subset of all of these. So A is a subset of B, A is a subset of C, and A is a subset of D. Okay, so all of these is a true statement. All of these. Okay. All right. So the next definition we should know is the union symbol. So here's we have the definition, the union, and that's what I'm going to put this in quotation marks because that's what it's referred to as, that's what we call it, the union symbol, which is this, like that. Okay. So A union B, let me just make sure that you know how this is pronounced. So it is pronounced A union B. Okay, that's how we pronounce it. And it is a new set. You take the union of sets A and B, you're going to get a new set. Okay, it is a new set that contains all, this is the key, all the members in sets A and B only once. So here is a very important note. In probability and statistics, A union B Okay? So in probability and statistics, that notation, A union B, also has this kind of interpretation. Any element that is either part of A or part of B or part of both A and B. So it means all of this, all of that, all of these is part of the union. It's basically everything in both A and B. Or both. Okay? So another definition we should know about is the definition of the intersection of two sets. Okay, so let's look at that. And I'm also going to put this in quotation marks. The intersection symbol, which looks like that. Okay. So this notation refers to any elements that are part of both sets. In other words, all common elements are part of the intersection of two sets. So only those elements that are common to both sets. Okay, common to both sets, very important. And of course, this notation applies to more than two sets. So if you have some elements that are common to 5 different sets, then those elements are the intersection of those 5 elements. Okay? They are common between all those sets. Okay, so after having talked about these definitions, we have more definitions coming up, but let's give a brief example for this union and intersection before we see other definitions. So suppose we have these two sets. Right? We define these two sets. Then, part A, we're asked to find A union B. Okay, that's what they're asking us. So A union B, let's remind ourselves, that's everything in both sets, right? All the members in sets A and B only once. Okay? So that would be then so that would be A union B. I'm going to put these in order. So 0 first, then 1, then 2. 3 happens in both, but we only need to list it once. And then 4, and then 5, and then, of course, 8. Okay? That's A union B. The other thing that you should know, this notation also is referred to with the phrase at least. So if in a word problem you see that phrase, at least this or at least that, the problem is giving you a clue that they're talking about the union of sets. Okay, so A union B is usually referred to as at least in word problems. Okay, and then part B, let's say they're asking us to find A intersection B, right? And we learned that, we just mentioned that this A intersection B are any elements that are common to both A and B, right? And of course, in this case, that would be 3 is the only element that is common to both sets. So A intersection B is equal to just 3. Okay? And by the way, you do not want to list this as just 3. You need to put the curly braces around this 3. A intersection B equals 3 is not the proper form of showing a set. A set has those curly braces around the elements of the set. Okay? So please don't leave these curly braces out. Okay. So let's go to the next definition, which is the disjoint sets. Okay, so definition. Disjoint sets, and this has another name, another very famous name. So disjoint sets are sets that do not have anything in common, and it also can be given this name, mutually exclusive sets. Okay. So these are sets that have no element in common. Okay? And so let's give an example of this. Suppose set A is 8, 20, and 33, and set B is -1, 2, and 10, then A intersection B is just the empty set. Right? They have nothing in common. So A intersection B is 0. You can even say 0. Or, well, there's nothing. The empty set, not 0, but empty set, or A intersection B is the empty set. Okay? Let me just remind you that notation, those two notations, refer to the empty set. Okay? Because those two sets have nothing in common. These are disjoint sets. Okay. So on to next definition. and the universal set, and I'll just add it, i.e. the sample space. So when I was taking these classes as an undergraduate, they referred to this as the sample space most commonly. But nowadays, textbooks also refer to it as the universal set. Okay? But they're the same thing. Or the sample space refers to all possible outcomes from a single random experiment. Okay? That's that. The other thing you should know is that in statistics, unlike electrical engineering or I suppose even mechanical engineering, I'm not sure about mechanical engineering, but definitely in electrical engineering, you have global convention that governs the sets of notations they use to refer to different things. But in statistics and probability, there is no such global convention for application of notations. So different authors use different notations to refer to the same thing. For example, notations, some authors might use the letter omega. So let me write that down. The sample space or the universal set is sometimes denoted as S, capital S, for sample space, or the Greek letter omega. In most books, I'd say in most books. Your book, the recommended textbook here, the recommended textbook uses the letter U. Okay, just be aware of it. It's possible that you see any of these letters or even other letters, but as long as that the author uses it as a sample space or the universal set, it means that that letter is representing all possible outcomes from a random experiment. Okay, it refers to the same thing. Let's give some examples of sample space. The universal set for flipping a coin is, I'll just call it S, is either a head or a tail, right? If you flip a coin 1 billion times, you're not going to get an outcome that is not a head or a tail. So these two outcomes form the sample space for flipping a single coin, either a head or a tail. That's a sample space. Okay, let's give another example. A six-sided die is as follows. 1, 2, 3, 4, 5, and 6, right? So if you roll a six-sided die, again, as many times as you like, billions of times, you're not going to get an outcome that is not in here, right? This is a sample space. It contains all possible outcomes from rolling a six-sided die. Okay? Let's give another example of a sample space. And for tossing a single coin twice is, right? And this time I called these last two examples S, but let me call this the sample space for this one with U, right? To denote the universal set. So if you have a single coin that is tossed or flipped twice, then what are all possible outcomes, right? You can get two heads, right? So that's one possible outcome, two heads. You can get the first one come up head and the second one as a tail, right? The first one a tail, the second one a head. Is that all? Or is there anything else we should add? Well, if you said a couple of tails, you'd be right. Right? That's all possible outcomes from tossing a single coin twice. If you toss a single coin twice, you're not going to have an outcome that is not part of this set. Therefore, this is the sample space or the universal set. It contains all possible outcomes from a single random experiment. Okay, so more definitions coming up. Definition of complementary sets. Complementary sets. These are sets that complement each other with respect to the sample space. Okay? So, but a complementary set should not have any element in it that is also part of the set it is complementing. Okay? So we'll give examples of that. Okay, the best way to show this is by just looking at some examples. First of all, let me give the notation for this. So, in this book, so remember that there's no global convention for use of notations in statistics. So in this recommended textbook for this course, the author uses a certain notation which other authors may not necessarily follow. Okay, so the complement of set A is denoted as A bar. So that is pronounced A bar, B-A-R, A bar, and it represents the complement of set A. So if this set was called B, this would be B bar, right? If this was C, this would be C bar, the complement of that. Okay, so that's the notation note. So suppose, so let's do an example over this. Suppose we roll a 6-sided die twice and obtain the following outcomes. Okay, these two outcomes, 1 and 5, right? So we ask, what is the sample space? What is the complement of A, of set A? Well, in order for us to determine what is the complement of A, or let me add, or what is A bar? Complement of A is A bar, right? That's the question. So in order for us to answer this question, we need to know what is the sample space or the universal set. Well, the universal set for rolling a 6-sided die is as follows: 1, 2, 3, 4, 5, 6. Okay, this is our sample space or the universal set. Right? So A complement, and so thus A complement or A bar is anything that is not part of A but part of the sample space. So 1 is there, it's not going to be part of the complement. 2 is missing from A, so it's going to be part of its complement. 3 is part of the sample space but not part of A, so it's going to be part of its A's complement. 4 is part of the sample space but not part of A, so it has to be part of the complement of A. 5 is part of the sample space, but it's also present in set A, so we're not going to list it because A complement should have anything that is part of sample space but not part of the set A. 5 is there, we don't list it. 6 is part of the sample space, but it's missing from A, so it has to be part of the A complement. Okay? So this is the answer to that question. Okay, so let's do a comprehensive example with what we've learned so far. Okay? Let's do a comprehensive example on that. All right. So suppose we have these sets. Suppose the universal set, so this is the sample space, U, universal set. Suppose the universal set is been defined as follows: 1, 5, 8, 10, 12, 14, 16, 19, and 22. So as far as this example is concerned, once you define the sample space, that means in the whole world, there are no other numbers but these, as far as this question is concerned, because that's our universal set. Okay, we assume there's no other number but these numbers that are listed as part of the universal set. Okay, then given that, then suppose we have A as 5, 8, 10, 12, 14, and 16. That's how we define set A. Let's define set B as 1, 8, 14, 19. Let's define set C as 8, 10, and 19. Okay, so that is our sample space. Okay, or the universal set. All right? Okay, so let's answer the following questions. I'll try to keep this on the screen as much as I possibly can, but this question has many parts, so I might go off this screen. Or I'm sure at some point it'll go off this screen. Okay, so for part A, we ask, is set B a subset of set A? What do you think? Is this set B a subset of set A? Right away you can tell no, right? Because 1 is part of B but not part of A. So right away, no. Okay. For part B, is A a subset of U? You know, the sample space. Is this a subset of, is A subset of the universal set? 5 is there, 8 is there, 10, 12, 14, 16. So yes. Okay. So let me put this to save space and to try to keep everything on the screen as much as I can. So part C, is set B a subset of set U, or the universal set? What do you think? B, 1, 1, 8, 8, 14, 14, 19, 19. Yes. Okay, so it's definitely B is a subset of set universal set U. Then we can ask for part D, is C a subset of U? Again, yes, right? 8, 10, 19. So once again, yes. Okay. Then let's ask for part E. We want to find, for part E, we want to find A intersection B. Okay, that's the question we have. So A intersection B is referring to any elements that are part of both A and B, right? 1 and 5, no. 8, yes, 8 is there, part of both. 10 and 14, 10 is not here, 12 is not here, 14 is here, 16 and 19 are not common. So A intersection B would be 8 and 14 only, right? So 8, 14. Part F, we ask to find A union B. That's what we want to find. A union B is everything in A and B, right? Everything in A and B only once. So looking at those, what do we get? We get 1, we get 5, we got to list them in order, right? 8, 10, 12, 14, 16, and 19, right? All right, that's that. Then we want to know is A intersection B a subset of A union B? Okay, we have both. We already have figured both. This is A intersection B is here, 8 comma 14, and A union B is here, all of this. So this question is asking, is A intersection B, that one, a subset of this? Well, let's check. 8 is here, 14 is here, so yes. Okay. Then we want to find, let's call this part H, and I need to move this up so you can see this. So H, we want to find intersection of C and complement of intersection of A and B. Okay, so we want to find the intersection of C and complement of A intersection B. Okay, so we already know this, right? We already know A intersection B is right there, 8 comma 14, right? So the complement of A intersection B is anything that is not part of A intersection B, but it is part of the sample space. Okay, and the sample space is up here. That's our sample space. So once again, the complement of, we're trying to find this, and then we take the intersection of C with that. But we haven't found the A intersection B bar yet, the complement of A intersection B. We're going to need to find that. So we know A intersection B is this. So A intersection B bar, the complement of that, is anything that is part of the universal set or the sample space, but not part of A intersection B. That is anything that is part of the sample space, but not here. So 8 and 14 need to be excluded. Everything else in the sample space should be included. Except A and 14, everything else is included. So I'm going to write it down. So we already know that. And so therefore, or thus, A intersection B bar is equal to 1, 5, 10, 12, 16, 19, and 22. So I'm going to double check this with what I already have. Yep, okay. So that's A intersection B bar. Now we need to take the intersection of set C with that, which is what they're asking for, right? So, and C, it's off the screen, so I'm going to write it down so you can see it on the screen. So C, we were told, is 8, 10, 19, right? So this, then, this, you need to find, so C intersection of A intersection B bar, you need to take the intersection of this with intersection of the set that is above it. So, do we have 8 anywhere there? No. 10, yes, we have 10. And then 12, no. 16, no. 19, yes. There. Okay. So this is the desired outcome or set. Okay, just 10 comma 19. Okay, so let's do another example, another part. Let's call that part I. So part I, we're asked to find C bar union A intersection B. Okay, we're asked to find that. Well, we already know A intersection B, right? Right there, A intersection B, we found it in part E. It's 8 comma 14. If you didn't have it, you would need to find this first before you can look at the union or take the union of C bar and the. So basically, we need to know what C bar is. We know what C is, but not what C bar is, right? We need to find C bar. We need to find A intersection B. We already have it. And then once we have these two, we take the union of them. Okay, so let's do that. So C, I'm going to write it down again because it's off the screen. Well, you have it here. Okay, so C, it's okay. I'll just write it down again. It's no big deal. So 8, 10, 19. So that's C, right? Therefore, C bar will have to be anything, any of these elements that are not part of C, but part of the sample space. Okay? So C is comprised of 8, 10, and 19. 8, 10, 19 is C, right? So C bar is all the other elements that are not in C. So 1, 5, 12, 14, 16, and 22. So let's write those down. So C bar is 1, 5, 12, 14, 16, and 22. Okay, just making sure here. Okay, that's that. So that's C bar. So we got this. We already know A intersection B is equal to that, right? 8 comma 14. Like that. And therefore, now, given all of this, we have C bar, we have A intersection B. Now we can take their union. So C bar intersection, sorry, no, I need to correct that. And not intersection, union, right? It's a union. So union, C bar union, A intersection B, would be everything in these two sets included. So we're going to have 1, 5, 8, 1, 5, 8, 12, 14, 16, and 22. Okay, so this is that result. Okay, I hope this is starting to make sense. Let's do one more. Let's do one more, part J. I wanted to include everything on one page, but I couldn't. And so it's okay though. So part J, we want to know we want to know this. A bar intersection C bar. Okay? Okay, so let me write down what A and C were defined as first, because it's off the screen, so we can have it in front of us. So A was defined as 5, 8, 10, 12, 14, and 16, right? So that was A, and therefore A bar. So therefore A bar, it's going to be any number that is not part of A, but it is part of the sample space, right? So let's see. So 1 would be one of those numbers, right? 1 is not part of A. We're trying to determine A bar, or complement of A. So 1 is part of the sample space, but not part of A. So we need to include it in A complement, comma. 5 is here, part of A. 8 is here, 10, 12, 14, 16. But 19 and 22 are part of the sample space or the universal set, but they are missing from A. So those numbers have to be part of the complement of A. Because A bar complements A in order to give us the sample space, the full sample space, right? So 1, comma 19, comma 22. So that's A bar. So we also need to find C bar. To do that, let's list C again. C is 8, 10, and 19, right? Therefore, C bar, or complement of C, is is anything that is part of the sample space or the universal set, but is not in C. That's why C bar complements C, right? To give us the full universal set. So let's see. 1 and 5 are not part of C, right? They're not here. So they must be part of the complement, 1 and 5. What else? 8 is there. 8 is there. 10 is there. 12, 14, and 16 are not there, are not here in C, so we must include them as part of the C complement. And then 19 is here in C, so we should not include it in C bar. And then 22 also, right? 22 is missing from C, but it's part of the sample space, so we include it as C bar. So we have 1, 5, 12, 14, 16, 22. Okay? So now that we have A bar and C bar figured out, we can take their intersection. So, therefore, A bar intersection C bar are any elements that are common to both sets. So 1, 1. Right? 5 is not there, so we can include it as part of the intersection. 12 not there, 14 not there, 16 not there, 19 not there, 22 is there. So 1 and 22 are the intersection between A bar and C bar. Okay, I hope this made everything clear. Okay, so the next thing we have to look at are the Venn diagrams. Okay, I want to go to even though I have plenty of space here, but that's not going to be enough for me to show all the examples. So it's okay. So I'll just move to a new page. So we want to understand Venn diagrams. We will have to say more about Venn diagrams in future sections though. But here we're just going to introduce it and do a few examples. So one thing that you should know, Venn diagrams are used only with dependent random outcomes. I say it now because I just want to bring this to your attention, even though we have not yet gotten to this point where we can talk about dependent, independent events. We haven't gotten that far yet. We will. But at this point, I just want to mention it very briefly that Venn diagrams are used only with dependent events, not with independent ones. Okay, so independent events cannot be shown using a Venn diagram. Okay, so let's see examples of notations connected with Venn diagrams. Okay, so suppose we have these 3 events. We can have 2 events or 3 or even more, 4 events. So I just wanted to begin with 3 events. This is what a Venn diagram usually looks like that. And like I say, you can have 2 circles. You don't have to have 3 circles. 3 circles means 3 sets of events. So A, B, so set A, set B, set C, and of course this box in totality is the universal set. So the universal set is everything inside the box, including A, B, C, including the part of this box that is not part of A and B and C, right, out here. Okay, so this is this piece is the sample space. So the box represents the sample space or the universal set. Okay. Then there are various derivations of a Venn diagram we can talk about. For example, how would we look at, so if this is our original Venn diagram, let's say this, draw A intersection B. Okay, in other words, in this Venn diagram, show where A intersection B would be. Okay, let's do that. So I'm just going to try to duplicate this as best as I can. All right, so then we have U out here, set A, B, and C. So A intersection B would be this piece, the overlapping piece between A and B. That would be A intersection B. In other words, if this is the notation, this is the Venn diagram interpretation of that notation with respect to this original Venn diagram. Okay, let's draw C bar intersection A. Okay, suppose we want to draw that. Well, first of all, let's draw the 3 circles again. Okay, so these should be duplicates. I mean, if they're not, it's my fault, but these are the same circles and the same Venn diagram. So A, B, C. So C bar would be everything outside of C, but inside the box, right? Because the box is the sample space, so we cannot go outside of this box. Okay? So C bar is everything outside of this circle C. But we want to take the intersection of that with set A. Anything that is outside of C but has an intersection or overlapping piece with set A. Well, that would be just this piece right here. Let me draw this as best as I can. I didn't want to cover A, but looks like I can't help it now. but that is, and let me write it here. So that is set A, okay? That is set A, and C bar is everything outside of this circle. That's C bar, but we need to take the intersection of that with A, with set A, and that would be that. Okay? And I also, well, I also should take, I just saw that, so I need to cover up this piece as well, right? If I do that, it's going to cover that line, but I guess it doesn't matter. It's okay. So, because that piece is part of A, but not part of C, and it's part of C bar. So we need to also expand that here. Okay? So C bar, intersection A is that piece. Okay. So C, part C, we want to draw A intersection B intersection C. Right? We want to draw that. Okay. Okay, so let me try to duplicate that again as best as I can. Like that. And then, of course, this is the sampler space, the whole box. Then A, B, and C, right? So A intersection B intersection C, that's the area common to all three, right? When you look at this, what region is common to all three sets? Is it here? Here? No. That region is common to B and C, but not A. How about here? No, that's A and C common, but not B. So the only region that is common to A, B, and C is this piece here. This piece here, right? Right there. We shade that piece to highlight that. Okay? All right. So let's draw A union B union C. Okay, let's draw that. Okay, so we have A, B, and C. So A union B union C is everything in A, B, and C, right? So then this would be, that's probably too easy, right? So A union B union C is everything in A, B, C. So I could just go ahead and let me grab a piece of scratch paper. So if you wanted to just do that, let's change this a bit, but I'll tell you how we're going to change this. But if we wanted to just draw that, we could just do this. Right? We could just do and A union B union C would be everything in all the three circles. But that's too easy, right? Let's change that a bit. So I just want to draw, for those of you who might be interested, that's this, what you see here is A union B union C. But that's too easy, so let's change it a bit. Let's make it like that. Let's make it A union B union C bar. Okay? In other words, the complement of this. So I just changed it. So we're not looking for A union B union C anymore. We're looking for A union B union C bar. So the complement of this. What would be the complement of this? That's what we need to draw here. Do you see it? So the complement of this is everything outside of the circles but within the box. So it'll be this. It'll be that. All of that is A union B union C bar. So this bar changes the diagram, right? So everything outside of this like that. So all the blue shaded region is A union B union C bar. So that region that I've shaded is the complement of this region, right? Which would be, this would be A union B union C. This is the diagram for that. Okay, but we're looking for the bar, the complement of that, which would be everything outside of the circles, but within the box. Okay? Let's do one more, maybe. Yeah, let's do one more. So we want to draw C bar. We want to draw that. Okay, so here are the three circles again. So C bar is anything outside of C, but within the box, within the sample space. So C bar would be all of that. Oops, I should not go outside of the box. So let me correct that, guys. I should not go outside of the box. So that's the box. I need to stay within that, okay? But outside of C. So that is C bar, okay? The previous example that we did, that we went up to J, part J, gave us the same thing. We did the same things, but using sets, right? Using set notations. But we're doing the same thing. We're similar examples, but this time we are using a Venn diagram. So different representation, but essentially we're doing the same thing. We're trying to find the union, intersection, complement of sets. Okay? But this ink, this blue ink, should fill everything outside of set C. So that is C bar. All the way to the edges. Okay? Like that. All of that included. All of that too. Okay? That's C bar. And here as well. Okay, so we've come to the conclusion of our first discussion of probability concepts. The future sections will cover different content, but we will use some of this in the coming sections. And thank you for persisting through this video. And for now, have a nice day, and I'll see you again next time.